Hi, I'm Lana, and I'm going to be talking about data structures today. So as we talked about, C is a language where you have to strictly allocate memory. And so a data structure you might have already learned about is an array. And an array is a strip of contiguous memory, meaning that if you're looking at a memory strip in the computer, every element in the array is next to each other in the memory. Now this isn't always realistic, because what if we want to, for example, update an array with that and make it a bigger size? This is difficult because we might already have something stored next to the array, which is why we make data structures. Data structures are ways of storing data using pointers. And a pointer would be an address to a specific memory. In C, we represent pointers using an asterisk, which basically just is the address to where the information is stored. So if we have a data structure, then we can use these pointers to go from one piece of our data to the next, even if it's not necessarily next to the previous piece of the data. So we can store our data in different pieces in the memory, which allows us to update the memory more dynamically and create more flexible structures. So the first structure we can talk about is a linked list. And a linked list is the most simple example of a data structure using pointers. So if we have our first element in the list, then it has a value and a pointer. And that pointer goes to the next item in the list. So you can have your list like this, and each item will point to the next one. And this is really nice to do in C. We can call it recursively because each element will have a pointer to the next element. So you can so if you want to search for an element in the list, you keep on transcending the list until there's no pointer to the next object. And that would help you go through the whole list. But linked lists aren't that good if you're super picky about the order. So another thing you could do is called a stack. A stack is exactly what you think of as a stack in the physical world. So if you, for example, are stacking plates, if you have one plate on the bottom, the next one's going to go on top. And the next one's going to go on top of that, right? So if you want to pop something off the stack, you're going to pop the top item first off, right? Because it's going to be the most recent thing you put on is going to be the first thing to come back off. Just like if you're stacking plates, you have to remove the top one. This is a good way to store information when your most recent information is your most relevant. On the other hand, we have a queue. A queue would be kind of like a line. So let's say you're at a restaurant and you want to store the orders in a data structure. You'd want the first person to put their order in to also be the first person to get their food. So if this is the front of our line, as we add more items in, they're going to go more towards the back. And if we remove an item, we're going to remove our first item first. So a stack and a queue are kind of opposite data structures. They both have the same operations. Push would be to push an item onto the stack or queue, so to add an item on. So if it was a queue, this item would go to the back, and that'd be our push. Another operation we have is pop. This would remove the top item like we saw here, and it would return the top item. We also have peek, where we can look at the topmost item on our stack, or queue, which would be opposite in either for the stack or the queue. Another good way to store data if we need to be doing a lot of searching is a binary search tree. Trees are data structures that look like trees. So you can have a node here, and it'll have pointers to its children. And this is useful because you can descend it in a shorter time than if you have a linked list, because then you have to go one item at a time. Search trees are good if we want to be storing things by rank. So one of the most common search trees is a binary search tree. If you remember the first CS50 lecture when David Malan tore the phone book and kept on dividing it in half to find something, that's a similar premise to a binary search tree. So for example, if you have a binary search tree that's ordered as a heap, then you're going to have this. It's going to satisfy the property where the smallest item is at the top, and each of the children is bigger than its parent. So if we have the smallest item at the top, we know these both would have to be bigger. And we know that these items down here would have to be bigger than these items still. So if we are looking for a specific number, If we're looking for a specific number, we know that we only have to do in binary time because we can keep on taking the path that will lead us towards what's bigger or smaller than where we were before.